And we're back, so welcome back everyone. Today we're going to be talking about the probability density function, which is similar to the probability mass function we went through last time, except it relates to continuous random variables. So first I want to look a bit at what exactly that means, and I think the best way is to take an example again. So let's say that I'm thinking of a number between 0 and 1. And it could be any number, right? So it could be a half, it could be a quarter, but it could be mad numbers with infinite decimal places. For example, pi over 10. Well, we can represent that number that I'm thinking of as a random variable. So over here, let's say we will call it x. So this is a number that I am thinking of, and it will be in the range 0 and 1. And that's how you write that. So the key thing to note here is that there are actually an infinite number of real numbers, between the numbers 0 and 1, right? Again, because you can pick numbers to an arbitrary degree of decimal places. And that makes it difficult to use a probability mass function, but let's give it a go anyway. So let's try to use the probability mass function to model this. And if we remember from last time, this will be valid if the sum of the probabilities over all possibilities is 1. So the sum of all the probabilities over all possibilities should be 1. And let's take a look at two scenarios. So the first will be when the probabilities of all the possibilities are positive, so greater than 0. Again, for the range of numbers that I'm thinking of between 0 and 1. So let's try and prove this condition. So we take the sum over all possibilities of the probabilities of those possibilities, and we can say that that is the probability, or that I think of as 0, or the probability that I think of the number marginally greater than 0. So 0.0001. So this is infinitesimally larger than 0. So there's actually an infinite number of decimal places here before we actually reach the 1. And this kind of continues until we eventually would actually reach the possibility of a 1. So something to note here is that, again, there's an infinite number of possibilities. So we're summing the probabilities of those possibilities, which are all greater than 0. So you might notice that this sum would simply blow up to infinity, which is not what we want, because infinity isn't equal to 1. So the probabilities can't be greater than 0. Okay, fine. So how about we say that they are 0? So let's take a second scenario where the probabilities are all 0 for the same range. Here we go. And now let's do the same exact thing. We want to sum over all the possibilities of the probabilities of those possibilities, and we get the same thing where we take the probability of a 0 and then the probability of the number marginally greater than 0. So and then at last you would reach the probability of a 1. Except this time this is an infinite sum of zeros, because the probabilities are all 0. So this leads to, again, a 0 plus 0 plus and you just have an infinite number of zeros, which is 0. Again, this isn't really what we want. So we wanted this to be equal to 1. So because 0 isn't equal to 1, this probability function isn't valid. So clearly using the idea of the mass function isn't working. So what is the solution then? It turns out that you need to change. Oh, I've misspelled that. It turns out that you need to change your frame of reference to start thinking about probability densities as opposed to raw probabilities. And I'll explain that in a little bit over here. So we want to do probability density rather than probabilities. And another well, a synonym for this is likelihood. So probability densities or likelihoods. So let's formalize that a bit. So if we define the probability density function, it uses the same notation because it's still a probability function. So we would say fx of x. Again, this is relating to the random variable, which is the number that I pick between 0 and 1. And instead of being the probability, this is now the likelihood that the random variable that the number that I choose will be some specified number x. And let's put that in a box to show how important it is. There you go. So you can see that we've moved away slightly from the idea of probability and we're moving towards this idea of likelihood and probability density. So let's take this example further and draw it out graphically. Sorry if you can hear that, by the way, it's a train. But yeah, that's not a very straight line. So here we go. That's not a very straight line either. Yeah, that'll do. So the y-axis now represents probability density rather than probability. Again, it's the same notation though. And the x-axis represents the possibilities that there could be. So it would be between 0 and 1. Again, because I am picking a number between 0 and 1. And let's say that it's the probability densities is just flat. So this is called a uniform distribution with a value d across all possibilities. So what exactly is this idea of probability density? Well, if you think about normal density in physics, it relates to the idea of mass per unit volume, right? So kilograms per meter cubed. And in the same way, probability density of so the probability density, for example, over here, simply represents the probability over here per unit change of x, whatever this x represents, right? So I think you doing a couple of tests here will kind of clarify this a bit. So let's first look at working out the probability of a single possibility. Again, sorry, the trains. So we are going to choose a single point x. Let's say it's this point right here, right? This point x. And this point x has a probability density d that we've shown here graphically. And now we want to simply find the probability that the random variable will be this x. Well, since we've already said that probability density is probability over kind of change of x or unit per unit x, we can kind of see how we can rearrange this to just get probability, right? So if I try and illustrate that here, we could say that it should be the density, the probability that the number I pick is some number small letter x should be the density of that small letter x multiplied by the width or the range or the change, however you want to think about it, of x. So this kind of brings into light another interesting phenomenon where this equation is essentially finding an area, right? So we are trying essentially to find the area of some range, except in this case, the range, because we're looking just particularly at a single number here, or a single possibility, we're essentially trying to find the area of a line, which, as we think of it, has zero width. And so this delta x number is actually zero. So you would get the density times zero, which is zero. So actually, we get this interesting phenomenon where the probability of any single possibility is zero, right? But the probability, and let's go on to look at the probability of all possibilities though. So let's now look at what is the probability that x is between 0 and 1, right? Which is another way of saying what is the total probability that I pick any possibility, right? So this now would be the density of those possibilities. Well, I mean, because it's an area, sorry, let me undo that. So because it's an area, we're actually just trying to find the area under this entire graph, which in this case is simple because I've defined it as a uniform distribution, so it's flat. So in this case, it would simply be d times 1. So, which is d, right? So the probability of any possibility is d in this case. In general, it should be the total area under the density graph. However, we are in a unique situation where we can say, still, fundamentally, the sum of the probabilities of all the possibilities should be 1. This fundamental concept should still hold. So we can say that this should equal 1, and as a result, the density value must also be 1. There you go. So this is 1. So again, now we have kind of fixed the problem we had with the mass function, where the sum of the probabilities of over all possibilities is 1, but we still have this interesting case where the probability of any singular possibility is still 0. And the way we've gotten around that is through the use of this probability density. Now, let's write this down again a bit more formally. So I said before that probability is simply the area under a graph, right? So for example, say you wanted the probability between two values, right? It would be the area under the probability density graph between those two values. And in this case, it's been fairly simple because it's just essentially the area of some sort of rectangle. But say that this wasn't uniform. In maths, you can use integration, which is a calculus tool, to get the area under a graph. So actually now what we say is that the condition for the probability density function to be valid is that the integral over all possibilities of the densities should be 1. And this actually is the same thing that we said last time with the mass function, because this essentially says that the sum of probabilities over all possibilities should sum to 1. So I hope that that's been somewhat useful. And I guess I'll see you next time when we'll be talking about cumulative distributions. So I look forward to it and see you then.